Hello everyone, this is lecture 14, real vector spaces. So in this lecture, we're going to define a vector space and determine whether or not a given set is a vector space. So a vector space, in a layman term, is just a space of vectors, right? And in this space of vectors, you have two operations, that is vector additions and scalar multiplications. And using these two operations, you can actually check if the vectors in this set in a set satisfy certain conditions, or rather the 10 properties of vector operations. And if satisfy these 10 properties of vectors operations, then you can classify the set that given to you is a vector space. So again, let's look at the definition of this vector space. Again, in layman term, it's just a space of vector, but formally, if you let V be a set on which two operations, and these two operations are vector additions and scalar multiplications. Are defined if the following axioms are satisfied for every U, V, and W in the set capital V, and every scalar C and D, then you say that the set capital V is a vector space, or the set V is called a vector space. Right, so again, you given three different vectors, U, V, and W in a set capital V, and a set of scalars C and D. If you use this set of vectors in the set of scalars and check that all of this 10 following 10 properties satisfy, then you say that the set is a vector space. And you have seen this 10 properties already in the last lecture, right? So I break down into two different columns here. The first column related to the vector addition operations, and on the second column related to scalar multiplications operations. So the first property is that the sum is closed, or the vector addition is closed under is closed in V, right? So closer under additions. Let me use this color, so closer under vector additions. The second property is commutative properties of additions. Right, so U plus V is equal to V plus U, right? A commutative. The third property is the associative property. So U plus V plus W, right? So you do the additions of V and U, V and W first, and then add with U, or you do U plus V first and then add with W. It doesn't really matter. And this is the associative properties. The fourth property is that V has a zero vector, right? Is denoted as zero vector like this, such that, so SD means such that, for every vector U in V, right, you have that U plus the zero vector is the vector U itself, and this is called the additive identity. And the last property on this side of the column, so this side of the column related to vector additions. And the last property is for every u in the set V, there is a vector negative u, so which is the opposite directions of a vector u, such that, so SD again is such that u plus negative u is equal to the 0 vector. And this is called the additive inverse. All right. Now on the second column, you have properties related to scalar multiplications. So the first one is C times U is in V. So this is closer under scalar multiplications. The next property is distributive property. So if you have C times U plus V, it's going to be equal to C times U plus C times V. Again, what it say is that you can do the vector addition first and then scale the resulting vector, or you can scale vector U and scale vector V first and then do the vector addition on these two resulting vectors. So this is distributive property. The next property is that if you have two scale and you apply a sum of this two scale on a vector, so C plus D times U is equal to C times U plus C times V. D times U. Right. So this is also distributive property. The next one is that of C times D times U equal to C times D times U like this equal to D times C times U. This is associative properties of scalar multiplications. All right, so it just say that you have two scale and you want to do the product of this two scale first, and then apply the resultant scale on the vector U. Or you want to do the scale, apply one scale on the U, on the vector U, and then you have the resultant vector and apply another scale on the resultant vector. Okay, so this is associative of scalar multiplications. And the last property is that of scalar identity, right? So 1 times U is equal to the vector U itself, or the zero scalar zero identity. You have 0 times U is going to be vector 0. So the first one here is the scalar identity. Okay. So this 10 properties, again, you have seen this properties in the last lecture as well. We include this 10 property in the definitions because now we given a set, right? We are not quite sure if the set is the vector space or not. And to check that if a set is the vector space, you need two operations, vector additions and scalar multiplications. Now you have a set of vector, a set of scalars, and two operations, vector addition and scalar multiplication. You have to check that all the properties given here, right? So the 10 property need to be satisfied. If this 10 properties satisfied, then you say that the set is a vector space. Okay, one note here that a vector space consists of 4 entities. So a vector space consists of 4 entities. The first one is a set of vectors, so for obvious reason, right? because we are working with vectors and we want to know if the set is a vector space or not. So the set has to have vectors in it. The second entity is a set of scalars, right? Because eventually you need to perform scalar multiplication, so you need some scalars. Two operations, right? So vector addition operations. And number 4 is scalar multiplications. Okay, so this four entity for a vector space. You need a set of vectors, you need a set of scalars, you need two operations, vector additions and scalar multiplications. All right. Later on, we're gonna check if a set is a vector space or not. But for now, we're gonna write down some important vector spaces in linear algebra. So you may have seen some of this set already along the way in this course, and maybe you have seen these this vector space in other courses in mathematics as well. But so the first one R is the set of all real numbers, or R1 in one space, right? The set of all real numbers. You can have R2, which is a set of all the pairs. You have R3 is the set of all the triple. Right. We talk about n-dimensional vectors, or Rn. Right. This is set of all order n tuples. Okay, so you have seen this four set in the last lecture when we talked about one spade, two spade, three spade, or n space. So we working with two-dimensional vectors, three-dimensional vectors, or n-dimensional vectors. All of this set are vector spaces. We're going to look into a little bit of Rn later. Let's see what happened and see if this part of the vector space and why is that part of the vector spaces. All right, so the next set has the notation C, capital C, of negative infinity to positive infinity. So this is the set of all continuous functions defined on the real line. So for example, you have the function x, which is a continuous functions, and the domain of the function is from negative infinity to positive infinity. Or you can have, let's say, x squared or any polynomial functions for that matter. So but you can also have sine function, cosine functions. So those are continuous function in the domain of the functions going from negative infinity to positive infinity. And of course, there's infinitely many functions like that. So they all get clumped into this particular set of all continuous functions defined on the real line. You can have set of all continuous functions defined on certain interval. And that if that is the case, you use this particular notations, right? Set of all continuous functions defined on a closed interval from A to B. You can have a set of all polynomial functions, right? So it's denoted like this. This is set of all polynomial functions. All right, you have seen about the definitions of polynomial functions already in a few lectures ago. But if you want, you can write this is going to be a0, a sub 1x plus a 2x squared plus a 3x cubed, so on and so forth, and x to the power n, right? And so on and so forth. And you can raise that to any power if you like. So this is the set of all polynomial functions. or you have a little bit smaller set to be P sub n, just set of all polynomial functions of degree less than or equal to n. So in this case, the functions that you need to write is P sub n of x equal to a0 plus a1x plus a2x squared plus a3x cubed plus up to a sub n times x to the power n only. So for this particular function, you have a dot, 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 plus dot, dot, dot at the end, or after x to the power n, because you can raise to a certain power beyond degree n. But for this function, you just stop at x to the power n. Okay, so that's polynomial functions. Now you go to a matrix space. You have capital M of little m sub n. This is the set of all m by n matrices. Okay, and capital M of n times n, which is the set of all square matrices. Square matrices. All right, so all of this set that we look at here, right, given right here on this page, are vector spaces, right? Because it consists of a set of vectors, a set of scalars, in two operations, addition, vector addition and scalar multiplications. And if you check this 10 properties or this 10 assumes, they all satisfy the 10 properties, and therefore you can conclude that this set are vector spaces. All right, so let's check some of them. Right, so we're gonna do a few set. Right, so the first one is this set of zero vectors, right, or zero vector space. In example 2, we're gonna look at n-dimensional vector space and see what happened, so on and so forth. Okay. So in the first example, you have a zero vector space. So if you let capital V to be a set of zero vector, right? Only the zero vector is defined. And define the two operations that for vector additions, you have the zero vector and another zero vector, give you a zero vector. That makes sense. And you have a scalar multiple or on the vector 0, then you have a vector 0 again for all scalar k. Right. So any constant multiplying with a zero vector give you a zero vector back. So we just define the set of vectors. In this case, it's one vector 0, and a set of scalars k, two operations, vector additions and scalar multiplications. And we say that this is called a zero vector space. This is called the zero vector space. We're not going to spend time and check all the 10 properties given in the definitions. It's just that we look at this vector space and we focus on the 4 entities. Most of the time we focus on the 4 entities, that is set of vectors, set of scalars, vector addition, and scalar multiplications. And if you want to ensure that the vector, the set that given to you are vector space, you need to double check that all the 10 properties are satisfying. I want to give just a quick note here that is satisfying all the vector space properties. We're not going to spend time just doing one by one, right? It's very time consuming. All right, so the next vector space or the next set that we're going to look at is the n-dimensional vector space. So let capital B be Rn, capital V BRN and define the vector space operations on V to be the usual operations of additions and scalar multiplications of intervals. So that is, you have two vectors U and V, and you do vector addition like this. So U is n tuples, so U1, U2 up to UN plus V also n-dimensional vector, so V1 and V2 up to Vn. And if you do vector additions, you get that U1 plus V1, U2 plus V2, and UN plus Vn. So this is going to be in Rn as well. So this is closer under vector additions. If you have a scalar k, you perform that, apply that to a vector u. You have k times u1, u2 up to un is going to be ku1, k times u2, and up to k times un, and this is also in Rn. And this is called closer under scalar multiplications. Right. So we say that the set V equal to Rn is closed under vector additions and scalar multiplications. Because the foregoing operations produce n tuples as the end results. Right, because you have two n-dimensional vectors added together, the resulting vector is also n dimensions. Right. If you do scalar multiplications on the n-dimensional vectors, the resulting vector is also n dimensions. So therefore, you say that V is closed under vector addition in scalar multiplications. And again, we're not going to check the properties, all the properties of the vector space. Again, very time consuming. We're just going to focus on vector addition and scalar multiplications. So also a quick note here, V equal to Rn satisfies all the properties of vector space. Okay. Now, the next example, in the next example, you have vector space of infinite sequences of real numbers. So let V consist of objects of the form. So this vector is defined as follow. U is equal to U1, U2, up to UN, so on and so forth. So there's an infinitely many number here. Therefore, the idea of infinite sequences. So here we're going to define a little bit of U1, U2, and U. So we need to define that U1, what U1, U2, and UN, so on and so forth is going to be. So because we talk about infinite sequences of real number, so we say where, I'm using the colors here. So where U1 and U2, UN, so on and so forth, is an infinite sequence of real numbers. All right. So we're going to define, similar to the last two examples, we're going to define a vector addition and scalar multiplications. So we define vector additions and scalar multiplications. as follows. Right, you have two vector u and v. Right. Two vectors. These two vectors consist of infinite sequences of real numbers. Right. So u is u1, u2, un, so on and so forth, added with v1, v2, vn, so on and so forth. Then you obtain u1 plus v1, u2 plus v2, up to un plus vn, and then continue with the calculations. And for a scalar multiplications, k times u, you have k times u1, u2, un, so on and so forth. This is equal to ku1, ku2, up to kun, then so on and so forth. So you have two vectors of infinite sequences of real numbers added together. Then the sum is also consists of infinite sequences of real numbers. Similarly to the case of scalar multiplications, if you have a vector of infinite sequences of real numbers, then the scalar multiple give you a vector of infinite sequences of real numbers. Right? And we call this particular set, so V is closed under vector addition and scalar multiplications. And we define V to be R infinity, right? So when you have this notation, this is the set of, or the vector space of infinite sequences of real numbers, right? And of course, this set satisfies all the properties in the vector space definitions of vector space. A quick note here, it satisfies all the properties of a vector space. Okay, so you have look at three examples here related to vector space. The first vector space, we look at the zero vector space. The next one is n-dimensional vector space, and the in example 3, we look at vector space of infinite sequences of real numbers. So far we just worked with vectors. Now moving on, I'm gonna do some vector space of matrices. Right? So you have 2 by 2, consider 2 by 2 matrices. So let V, so again, in this example, we talk about vector space of 2 by 2 matrices. So let V be the set of 2 by 2 matrices with real entries. And take the vector space operations on V to be the usual operation of matrix addition and scalar multiplication. Right, so now you have consider two matrices, right? But the notations that we're going to use look similar to vectors. Right? So you have two matrices, or two by two matrices. So U plus V, matrix U is U11, U12, U21, U22, plus V is going to be V11, V12, V21, V22. Right, for the matrix additions, we're gonna just perform the calculations by adding the component wise of the two matrices. So you get U11 plus V11, U12 plus V12, here U21 plus V21, and U22 plus V22. Okay, so you have two by two matrices, right? And the resulting matrix is also 2 by 2. So this is so the vector V is closed in the matrix additions. For scalar multiplications, you get k times U11, U12, U21, u22. Right. So this is equal to ku11, k times u12, k times u21, k times u22. And again, for this scalar multiplication, you apply a scalar multiple on a 2 by 2 matrix, then the resulting matrix is also a 2 by 2. So the set V is closed under scalar multiplications. So we conclude that the set V is closed under matrix additions and scalar multiplications. Because the resulting matrices are 2 by 2. Right. So because this is a little bit different from vectors we have performed so far, so let's check a few properties or asymms in the vector space property. It's going to be very straightforward and very simple to do the calculations. So let me check the property number 2 or asym number 2 here. So asym 2, which is the commutative properties of additions. Property of additions. So that is u plus v is equal to u11, u12, u21, u22 added with v11, v12, v21, v22. Right. Now, is this matrices, right? You learned about the properties of matrices. Their additions are also commutative. So if you switch the order of this matrices, right, if you do v11, v12, v21, v22, added with the matrix u11, u12, u21, and u22, then you have v plus u. So it satisfies the second properties of vector space. Now let's check the asym number 4 or the property number 4, additive identity. So asym number 4, additive identity. So the identity of vector or of matrix additions is going to be, so u11, u12, u21, u22. So the zero matrix in this case, 0, 0, 0. Right? Now for the matrix addition, you just add the component wise together, or you get u11 added with 0, u12 add with 0, u21 add with 0, and u22 add with 0, and you get the vector u again. So it's just a couple of properties that you want to play around with. Of course, you can do the same calculation for the rest of the properties. But of course, this vector space of two, the set of 2 by 2 matrices is a vector space. Okay, so that is M, capital M of 2 by 2. Now moving on to the last example. In the last example, we're going to see that the set that we have is not going to be a vector space due to the weird setup of the scalar multiplications. Right. So we have a set, let V be R2, right, and define two operations. One is, of course, vector addition, and the second one is scalar multiplications. But for the scalar multiplication, we define a little bit different here. That k times u is not going to be k times u1, comma k times u2. But this scalar multiplication result in the second component to be equal to 0. I don't know what that is. I just know that this is the setup I want to have. And I want to know that does this set form a vector space or not? Right? So that means it has to be closed under scalar multiplication, closed under vector additions, and it satisfies all the properties of vector space. Right? So it's very simple. It's a lot simpler to actually prove that a set is not a vector space, right? Because you just need to find one condition or one property that it is not satisfying, then you can draw the conclusion that the set is not a vector space. But for now, let's consider the following example. That if U is equal to 2, 4, and V is equal to -3, 5, and K is equal to, let's say, +7, then you have the usual vector additions. U plus V is equal to 2, 4 plus -3, 5 equal to -1, 9. So that's straightforward. For the scalar multiplication, you can have K times U equal to 7 times U, right? But because of the setup for this particular scalar multiplications, you get K times U1, which is 7 times 2, right, 0. This is the setup, right? Again, I don't know what that is, but that is the setup. And I want to show that, or I want to know if this, using this particular setup, will we have a set to be a vector space or not? So for this particular scalar multiplication, you get the resulting vectors to be 14, 0. So the addition operations that we have here is just the standard one in R2, right? So this addition operations is the standard or the usual one from R2, but the scalar multiplications is not. Right. And the set is not a vector space. So the set is not a vector space because it fails to satisfy one of the properties of vector space. Right. And if you notice for the identity of scalar multiplications, you do 1 times vector U, then this is going to be 1 times U1, which is 2 in this case, and 0, right? And this is equal to 2 times 0, which is different from vector U. So therefore, it does not satisfy one of the properties of the vector space, and therefore you conclude that the set with these two operations is not a vector space. All right, so that's it for me. In this lecture, we talk about the real vector space. Look at the definition of the vector space. And for a vector space, there are 4 entities that you need to focus on. The first one is the set of vectors. And second one is the set of scalars. The third one is vector addition. And the last one is scalar multiplications. To identify if a set is a vector space or not, you need to, again, have this 4 entity, set of vectors, set of scalar, vector addition, scalar multiplications. And on the properties of vector space, all of this property need to be satisfied. If all of this property is satisfied, then you say that the given set is a vector space. If not, if one of the properties fails to be satisfied, then you say that the set is not a vector space. All right, so that's it for me. Please let me know if you have any questions. Thank you.